Hopital's rule is a rule that helps us evaluate limits of an indeterminate form of either 0 over 0, infinity over infinity, negative infinity over infinity, and infinity over negative infinity, or negative infinity over negative infinity, when those limits exist. Now, what Hopital's rule says is that if you have that indeterminate, one of those indeterminate forms, then the limit as x approaches your value c of f of x divided by g of x will be the same as the limit as x approaches c of f prime of x divided by g prime of x. That rule is one that we usually learn, certainly after we have learned about derivatives. And sometimes we've had those sorts of indeterminate forms of expressions that could be approached another way, and we've already found a method to do that. But now Hopital's rule just gives us an additional choice. What I'd like to show here is several different examples, some that don't require us to use Hopital's rule, some that do, and then an example of one that you could use either method of finding the limit of that indeterminate form expression. Let's get started. So the first one is to find the limit as x approaches 0 of 4 times cosine x divided by tangent of x plus pi over 4. Now here what we want to do is look at the limit as x approaches 0 of the numerator and denominator individually, using that property of limits that the limit as x approaches a value of a fraction can be written as the limit as x approaches the value of the numerator divided by the limit as x approaches the value of the denominator. And the reason we want to do that is just kind of see what sort of situation that we have. Because if we have a continuous function at the value that the x is approaching, then our limiting value will be the same as the function value there, embedded by the definition of a continuous function at a point. But if we don't have that, we need to figure out what case that we have and if the limit there exists. So here, the limit as x approaches 0, think about the value approaching 0 in the denominator. So as x approaches 0, x plus pi over 4 approaches pi over 4. And the tangent of a value approaching pi over 4 is approaching the value 1. So my denominator is 1, not 0 or infinity. Now in the numerator, I have a value of x is approaching 0, and the cosine of something approaching 0 approaches 1. And 4 times a value approaching 1 approaches 4. So this actually just becomes the value 4 over 1, which is a limiting value of 4. So it's just one of those basic limit questions that we had way back at the beginning of our study of limits, and it doesn't have an indeterminate form, so Hopital's rule isn't needed, nor is it applicable to this situation. Now when we write our answer, we want to write the limit as x approaches 0 of that expression 4 times the cosine of x divided by the tangent of x plus pi over 4. That entire original question that they're asking us is equal to our value of 4. Make sure whenever you're writing out the limit, you use the 3 components of it. The abbreviation to the word limit, so the LIM. You need to show what your limiting variable is approaching right underneath the LIM. And then you need to have the expression that the limit is acting on. Now, if you just try to write it without this expression, it's meaningless. The notation doesn't actually present what it is that they asked you to find. So you need all 3 components and then equals your answer. Let's do the next one. Well, here I have the limit as x approaches infinity of 9 times e to the negative x times the square root of x. Well, as x is approaching infinity, I have my e to the negative value approaching infinity. Well, this value is approaching 0. So 9 times something approaching 0 approaches 0. And then As x approaches infinity, the square root of something getting extremely big gets extremely big as well. And so that's times infinity. Now, 0 times infinity is not an indeterminate form, but it is one of those expressions that when we work with our operations that allow us to get an equivalent expression, it can be transitioned to an indeterminate form. So remember, for those, that would be like infinity minus infinity. You build and get common denominators most times. Put that as an overall fraction and see what's going on. 0 times infinity, this case, we want to rewrite this expression so it is a quotient. Now, the easiest way to think of this and rewrite it as a quotient is that if this is over 1 and this is all multiplication that we have, then the easiest thing to put into the denominator that would also be something easy to differentiate once we put it down there would be an e to the negative x in the numerator becomes an e to the positive x in the denominator. Remember that when you move a factor from the numerator of a fraction to the denominator, the sign of the exponent changes. So I really have 9 times, and I'm going to write that as x to the 1/2 power, and then my e to the x in the denominator. Now let's investigate. The limit as x approaches infinity of e to the x, well, that gets extremely big in the denominator. And as x approaches infinity, x to the 1/2 gets extremely big. Times 9 is extremely big. So I have an infinity over infinity case. So this is one that I can use Hopital's rule. So then that says the limit as x approaches infinity of the original ratio is equal to the limit as x approaches infinity of the derivative of the numerator divided by the derivative of the denominator. So I'm not looking at it as a quotient of two functions that I'm trying to find the derivative of, in which case I would need to use a quotient rule. This is a rule of limits that says that if you have an indeterminate form, then the limit as x approaches the value of the original ratio will be the same as the limit as x approaches the value of the derivative of the top function divided by the derivative of the bottom function. So the rates of changes ratio. So then in my numerator, focusing on that, that's 9 times, well, the derivative of x to the 1/2 is 1/2 x to the negative 1/2. And then in the denominator, I have the derivative of e to the x is just e to the x. Now, rewriting this so that we can see really what is going on with it and evaluate the limit, I have, well, 9 times 1/2 is 9/2. And this x to the negative 1/2, I'm going to take that in the denominator and change the sign on the exponent. So I have 9/2 over e to the x times x to the 1/2. And then certainly I could build this top and bottom by 2 so that it's not a complex fraction, but 9/2 is just a constant. It's just a number. So there's no variable x up there. I've written everything where it doesn't have negative exponents so I can make sure that I have a clear indication what's going on. So as x approaches infinity, my numerator stays fixed as 9/2, and the denominator gets extremely big. So this is not an indeterminate form. I can't use Hopital's rule again and expect to get any information that is absolutely correct from it. It's not one that the Hopital's rule applies to, but this is one that is just our limit rules from our previous work with limits. If the numerator is a fixed number and the denominator gets extremely big, think my 9/2 divide by 10, 9/2 divide by 100, 9/2 divide by 1,000,000,000. That fraction goes to 0. So my answer is the limit as x approaches infinity of 9 times e to the negative x times the square root of x is equal to 0. How about this last one? Here I have the limit as x approaches 4 of x to the third minus 64 over 2x squared minus 11x plus 12. Well, as x approaches 4, put in 4 for your x's in the denominator. So 4 squared using your order of operations. So 4 squared is 16 times 2 is 32. Subtract, well, 4 times 11 is 44. That's negative 12 plus 12. That gives me a 0 in the denominator. In the numerator, I have 4 cubed, which is 64, minus 64 is 0 in the numerator. I have an indeterminate form that I can then apply L'Hopital's rule to. So we'll have limit as x approaches 4 of the derivative of the numerator. Well, the derivative of x cubed is 3x squared, and the derivative of negative 64 is 0 for that constant term's derivative. And then in the denominator, I have 4x minus 11, and then my derivative of my constant term is 0. As x approaches 4, 4 times 4 is 16, and 16 minus 11 gives me 5 in the denominator. So again, I do not have an indeterminate form here. Now as x approaches 4 in the numerator, 4 squared, again, remember your order of operations. 4 squared is 16, and 16 times 3 is 48. So I have 48/5. Now you may have remembered this type of question from earlier work with limits. Because this is a polynomial divided by a polynomial, if 4 run through the polynomial gives out a 0, then x minus 4 is a factor. And again, if 4 run through the numerator polynomial gives me out 0, then x minus 4 is a factor of the numerator as well. So the other way you could handle this is looking at that in the work with our polynomials and actually factor the numerator and factor the denominator. In the numerator, our factorization is x minus 4 times x squared plus 4x plus 16. And the denominator is x minus 4 times 2x minus 3. So we would get our 2x squared minus 3x minus 8x is minus 11x plus 12. So I factored that correctly. And in the numerator, if you multiplied this, you would get the x cubed minus 64. So I factored that correctly too. If you don't remember how to factor those, you can use synthetic division to get your factorization. So just synthetically divide by 4 in the numerator polynomial and get the coefficients of the other factor there, and synthetically divide by 4 of the denominator expression and get your other factor there. So now these common factors of x minus 4 can be removed, because remember the limiting process is as you get infinitely close to 4, not right at 4. So it will have the same limiting value of this simplified ratio as I get infinitely close to 4 as it did with the original one. And then when I look at the limit as x approaches 4 of that x squared plus 4x plus 16 over the 2x minus 3, well, as x approaches 4, 2 times 4 is 8, so 2 times x approaches 8, then minus 3, the denominator approaches 5. And doing the same thing in the numerator, you'll have this approaches 16 plus this approaches 16 plus 16, so I get a 48 in the numerator. So I get, which I should, the exact same answer to my question by either doing the older method with factoring the polynomials or using the newer process of our L'Hopital's rule. And why did we have to wait so long? Why didn't we do L'Hopital's rule at the beginning? Well, we needed to learn about derivatives before we could learn a process that involves the derivatives. And so that's why L'Hopital's rule had to wait until after we learned how to do the process of differentiation. So then for this one, we have the limit as x approaches 4 of our x cubed minus 64 over 2x squared minus 11x plus 12 is equal to 48 fifths.